In the previous lecture, we discussed moment area theorems. Now we are going to use those theorems to calculate slope and deflection at certain points. So the question here says that use the moment area theorems and determine the slope at A point, that is here, and displacement at C, whereas EI is constant. Flexural rigidity for this beam is constant. If this is the elastic curve or the deflected shape, because of this loading, we need to determine this theta, slope at A point, and deflection at C point, delta C. So the first step is to determine reactions and write moment equations. To determine reactions, we can apply conditions of equilibrium, but in this case, if I draw a line here at C point, and if I notice the member is symmetrical about this line, that is, the leftward portion of the member is a mirror image of rightward portion or vice versa. So in this case, you can calculate the total load acting on the beam, that is 8 kilonewton, 4 plus 4 is 8, and half of it will be transferred to A support and half of it, that is 4 kilonewton, will go towards the right support. So RAY in this case is going to be equal to 4 kilonewton, whereas RBY is going to be 4 kilonewton as well. And since no horizontal force is acting on this beam, RAX is going to be equal to 0. After determining reactions, we need to write moment equations. To write moment equations, we are going to cut sections. So how many sections do we require to write moment equation for this beam? You need to cut a section before a point where change in loading occurs. So if I move from left to right, I have this reaction over here. Then after this reaction, there's point load acting here. So there's a sudden change in loading. So I need to cut a section here. Let's name this section as 1, 1. And let's mark this coordinate as x1. So after this point load, where does the change in loading occur? It happens over here. So we need to cut a section before this. So let's call this section as 2, 2. And let's name this coordinate as x2. Similarly, if I start moving from this point load, I can see the change in loading or the sudden change in loading occurs at B point. So again, I need a section here, section 3, 3. And again, let's call this coordinate as x3. Okay, to write moment equation, separate this part of the member from the rest of the structure. So section 1, 1-1 starts from 0, x is greater than or equal to 0, and x is less than or equal to 2. So this section would help you draw the moment diagram from A point to this point load. And in order to write moment diagram, just separate this member on the left hand side of the section and write moment equation. And let's assume the moment acting over here at this section acting in counterclockwise direction. And we have this 4 kilonewton force acting at pin support. In order to write moment equation, sum the moment about this 1, 1 section and take clockwise moment as positive. Okay, so we know that this coordinate, we called it as x1. And this force, 4 kilonewton, is creating a clockwise moment about this section 1, 1. So this is going to be positive and it has a momentum of x1. And we have this moment which is acting in counterclockwise direction. So this is going to be negative. And we don't have any other force creating moment about section 1, 1. So this is going to be 0. And if I simplify this, m from here is coming out to be 4 x1. So this second section will help you draw the moment diagram section 2, it starts from 2, x is greater than or equal to 2, and x is less than or equal to 6. 2 plus 4, this is 4. The distance between the 2 point load, if you calculate it, is equal to 4. So this is going to be 6. We are measuring x from here. So the minimum value of x is equal to 0 at a point, and maximum value of x is equal to 8 over here. And for this point, x is equal to 6. Again, separate this member, leftward portion of member, from the rest of the member about section 2. Again, for writing moment equation, apply summation of moment, but this time about 2 section, and take clockwise moment as positive, and this force is creating a clockwise moment about this section, hence positive, and it has a moment arm of x2. And what about this one? This force is 4 kilonewton, this force, and it has a moment arm of x2 minus 2. So if I deduct 2 meter from this x2 coordinate, what would I get? I would get the moment arm for this 4 kilonewton force, and this force is creating counterclockwise moment about this section, so this is going to be negative, and it has a moment arm of x2 minus 2. And we have this moment which is acting in counterclockwise direction, hence negative. And if I write moment equation, okay, now for the last section 3. Again, repeat the same procedure. Separate the leftward portion of the member about this section from the rest of the structure. And as discussed earlier, this distance between the point load is 4 meter. Now, before writing moment equation for 3 section, let's first try to write the moment arm for each of the force with respect to this section. So this 4 kilonewton force has a moment arm of, if I deduct 2 meter from this x3, then I would get the moment arm for this force, which would be x3 minus 2. And what about this force? What would be the moment arm for this force with respect to section 3? So if I deduct 2 plus 4, 6 meter from x3, then I would obtain the moment arm, that is x3 minus 6, of this force with respect to section 3. To write moment equation, follow the same procedure. Apply summation of moment at 3 section, and take clockwise moment as positive. So this force is creating clockwise moment, this is going to be positive, and these 2 point load are creating counterclockwise moment about this section, and this force has a moment arm of x3 minus 2. So this is going to be negative for x3 minus 2, and this force is also going to be negative, and it has a moment arm of x3 minus 6. And this m moment is acting in counterclockwise direction, and this is negative. M is equal to, now after writing moment equation, we are going to draw moment diagram as well as M over EI diagram in the second step. So the section 1 will help you draw the bending moment diagram from a point to this point load, whereas section 2 will help you draw the bending moment diagram in between these 2 point loads, 4 kilonewton and this 4 kilonewton here. And section 3 ranges from x is greater than or equal to 6 and x is less than or equal to 8. And remember that in order to draw a bending moment diagram, you need to insert values in between these 2 limits in this equation. You can't go beyond these limits. So you can't substitute x equals 3 in this equation. To draw a bending moment diagram, I'm going to insert certain values of x in this equation. So I'm going to insert 0, 1, and 2. And after substituting these x values into this equation, m comes out to be And for this equation, let's take interval as 2, 4 and 6. And again, substitute these x values into this equation, yields us in the similar manner. Fill up this table for section 3.3. After calculating these points, plot it on this graph. On x-axis we have x coordinate and on y-axis we have moment values. Okay, let's mark some scale. So at x equals to 0, m is equal to 0. And at x equals to 1, we have, so 1 would be somewhere here, and we have m equals to 4. And at x equals to 2, we have moment value equals to 8. Similarly, plot other points. So this is your moment diagram for this question, and your moment value here is equal to 8 and here is 4. If I divide all values of moment diagram with EI, flexible rigidity, then I would obtain M or EI diagram. Okay, now we are in a position to apply the theorems of moment area method. Okay, the objective in our question was to determine delta C, that is deflection at C point, and slope theta A, that is the slope at A point. So if this is the elastic curve for this loading, for this beam, then this is theta A, and this is delta C that we are interested in finding out. And let's say this is the slope extending from A point. Now first we are going to try to determine this theta A. So theta A, and in order to find this theta A, we need to apply a second theorem of moment area method, which says that in order to find the vertical deviation at any point on the elastic curve from the tangent extending from another point, if you want to find this TBA, you need to take the moment of this M or EI diagram with respect to this point. So if I take the moment of this trapezoidal shape with respect to this point, I would obtain this TB/A. So let's start by calculating TB/A, and this is equal to the area of trapezoid multiplied by x1. Let's call this moment arm of this trapezoid with respect to this point as x1, and we know that the area of trapezoid is equal to the average of the bases. So there are two bases, the smaller one and this larger one, and this is 4 meter and this one larger one is 8 meter. So 4 plus 8 and multiply it with the altitude of the trapezoid. So the altitude of the trapezoid is 8 over EI. And the moment arm for this trapezoid is equal to 4 meter, half of the beam. Multiply it with by 4. So TBA, if you solve this, is coming out to be 192 over EI. Okay, after finding this TBA, if you apply a trigonometric relation to this triangle, to this right angle triangle that I'm pointing towards, tan theta A is going to be equal to perpendicular GB slash A upon base, and the base is equal to 8 meters. And one more thing, tan theta A is equal to theta A, because this theta A is really small. So TBA from our calculation was coming out to be 192 over EI divided by 8, and theta A from here is coming out to be equal to 24 over EI. Okay, so theta A is equal to 24 over EI. After calculating theta A, now we need to determine deflection at C point. In order to do that, we need to calculate this vertical deviation of C point on the elastic curve measured with respect to the tangent from A point, that is TC slash A. And let's call this point as O and this point as O dash. And in order to find delta C, we are going to use the property of similar triangles. So we have two triangles here, ACO triangle and ABO dash triangle. So we have triangle ACO and triangle ABO dash. And if I write the ratio of the perpendicular upon base for both of these triangles, for triangle ACO, the perpendicular is delta C plus TCA. So delta C plus TCA divided by the base, and this distance is equal to 4 meter. And for ABO dash, the perpendicular is TB slash A, and the base in this case is equal to the total length of the beam, which is 8 meter. And in this equation, if we look at this term, we calculated it previously and it was equal to 192 over EI. And if we calculate this term TC slash A, we would be left with only one unknown in this equation, and we can solve it. So let's try to determine this TCA. And in order to determine this TCA, we need to take the moment of M or EI diagram with respect to this point. And we are going to take the moment of M or EI diagram lying to the left of this point, because we are measuring vertical deviation with respect to the tangent from point A. So let's separate this shape into two regular shapes, that is triangle and this rectangle. And let's call this triangle as A1, and area of this rectangle is A2. Let's call the moment of this triangle with respect to A point as X1, and this rectangle as X2, moment arm of this rectangle as X2. So TC slash A is equal to A1 X1 plus A2 X2, and A1 is equal to the area of triangle, which is equal to half into base into altitude. Base is equal to 2 and altitude is equal to 8 over EI. And X1 here is equal to, this distance is 2 meter, and this is equal to 2 plus 1/3 of 2. If you notice, this distance is equal to 1/3 multiplied by 2. So if you add this distance to 2 meter, you'll obtain the centroid of this triangle with respect to this point. Now area 2 is equal to 2 multiplied by base multiplied by height. And height in this case is also equal to 8 over EI. And x2 is going to be equal to half of this 2 meter. So 2 upon 2. And if you solve it, it's equal to 37.33 over EI. Okay, let's call this as equation number 1. Then equation number 1 implies that delta C plus TCA, which is equal to 37.33 over EI divided by 4, is equal to 192 over EI upon 8. And if you solve this from here, delta C is equal to 58.67 over EI. And there you have it. We have deflection at C point equals to 58.67 EI and theta A equals to 24 over EI. And we're done. Thanks for watching till the end.